Hi everyone, welcome back. I'm Celso Viana and this is my contribution to the third Geometric Analysis Festival. This is lecture number 2. So in this lecture video, I will continue discussing the problem of classifying stable constant mean curvature surfaces. This time I will focus on three manifolds where we have specific features, two-dimensional features that are very useful in studying this classification for stable CMC surfaces. So some of the results work in generality, but I will restrict in this video to space forms, and at some point I will also focus on space forms of positive curvature. And the main reference will be the real projective space RP3. Okay. Essentially, what we want to do in this video is to discuss some ideas and key ingredients in the proof of the following theorem of Ritore and Ross in 92. So first, before we describe this theorem, so let me describe a little bit more about the notation. So here sigma 2 will be a compact Riemann surface that will correspond to a two-sided immersed surface inside a space form M3C. So C here denotes the sectional curvature of our space form. So it can be either 0, 1, and minus 1. Okay, and so in this theorem, as you can see, there is the first part which concerns a topological restriction on stable CMC surfaces when the sectional curvature is positive, so spherical space forms. So in that case you have a topological restriction. And the second part here corresponds to the geometry of stable CMC surface of genus 0 and N1. Okay, and so we would like to discuss the proof of this result, and then of course that will lead us to a characterization of isoperimetric surfaces in the real projective space RP3. Right, so let me start with a topological restriction that appears here. So it will be important that our space form has positive curvature, as will become clear in the argument. Okay, and so what kind of test functions can you use in this setting, right? So in this setting we don't have conformal vector fields as in the simply connected space form. So what kind of test functions can you use to study the problem? So in this case, we have this famous Hashio Trick, which is a very important trick in geometric analysis that has been used for many purposes. And the reason it is useful for our problem is because essentially the trick gives you a conformal map from your surface to the round sphere with a degree bound in terms of the genus of the surface, right? So since you are dealing with a conformal map, you can translate that information as an upper bound for the Dirichlet energy of this map. The Dirichlet energy of this map is then bounded by the genus, by a quantity that depends on the genus of the surface. Okay, and so a bound like that is very useful for the stability inequality, right? So what we want to do now is to use the coordinate functions of this map psi in the stability inequality. So the only thing that you need to be careful at this point is whether the coordinate function satisfies the volume preserving condition, right? So the integral must be 0. And that's the nice thing about the Hashio trick. So essentially it says that up to conformal transformation of the sphere, you can change your conformal map by composing with a conformal transformation such that the new map will have average 0 over the surface. Actually, you can prove that it has average 0 when you use any positive function multiplied by the volume element in your surface. So in our case, we are using the function 1. Okay, so essentially, if you do that conformal transformation and you compose it with our map psi, you are not going to change the conformal energy, and so that's how the method works. Okay, so using that trick, now you can use the coordinate functions and the stability inequality, and since the map goes to the sphere, the norm of this map is 1, right? And so in the left hand side you get just a quantity that depends only on the geometry of your surface, and for this part you can study through the Gauss equation, which is written here, and an application of the Gauss-Bonnet theorem. So the left hand side can be estimated in terms of geometric data and the genus of your surface. On the other hand, in the right hand side we also have the upper bound in terms of the topology of the surface, and now you just need to confront those two information, and the inequality you get is the one that appears here. Okay, so if you look at this inequality, what you can see is that the left hand side is positive, right? It's a positive quantity, which forces the right hand side to be positive as well. And if you look at this expression, you're going to see that the genus cannot be that large, because that will give you something negative. And so the topological restriction comes from this fact. And I just want to highlight that I use the positive curvature crucially in this argument, right? Okay, so that gives you the topological restriction on your surface, and if you carry out the details, you're gonna check that the genus is at most 3. The genus is at most 3. It can be either 0, 1, 2, or 3. Okay. Moreover, you also get a estimate on the area and the mean curvature of your surface, a Willmore type estimate for your surface. Okay. So a couple of remarks before we move on. The first remark is that 2 that appears in this result is something that is natural when you are studying surfaces in spherical space forms, and the reason is because 2 counts for the fact that the Higger genus of these 3 manifolds is 2 or 1, right? 1 corresponds to lens spaces. So there are examples of variational surfaces, such as minimal surface of index 1, which has a similar variational characterization and has genus 2. Okay. The number 3, on the other hand, is something that you might like to rule out, but it's still 3 is sharp in a way, because if you look at the border case, which corresponds to flat spaces, then there are examples with genus 3 there. Okay, so this was the first remark. And the second remark is that if you are interested in hyperbolic 3 manifolds, then the left hand side in the inequality above can be negative, right? And so there is no topological restriction for stable CMC surfaces in hyperbolic 3 manifolds. And in fact, you can construct one of each genus in the right spaces. Okay. Right. So now let's focus on now that we have the topological restriction. So let's focus on the real projective space, and let's try to rule out these genus 2 and 3 situations. Okay. And the way we do that is just by exploring this Willmore estimate that appears here. Okay. So if you are in RP3 and you look at the pre-image of your surface in the sphere, then you're going to get an upper bound for the Willmore energy, which will be 4 pi, right? Because the order of the fundamental group is 2. On the other hand, in the sphere, we know a lower bound for the Willmore energy, which was proved by Willmore in the 60s, right? And so if you compare those two inequalities, of course, you're going to get a contradiction, and that's how you rule out genus 2 and 3 in the real projective space. Okay, so you can explore a little bit more this argument, and you can use the groundbreaking work of Marquez and Neves, which improves the inequality above. When the surface has genus at least 1, then the Willmore energy is at least 2 pi square, right? And so if you use that beta estimate, you can go back to the previous argument and you see that you can extend the analysis to other spherical space forms, more precisely those with a fundamental group of order 3. So that corresponds to the lens spaces that appears here. So this is an observation that shows an interesting application of the Willmore conjecture after Marquez and Neves. And so in these spaces, real projective space RP3 and the lens space of order 3, stable CMC surface can only have genus at most 1. Okay. So now let's discuss the geometry of these genus 0 and genus 1 surfaces. Okay, and I think it will be useful to look at this argument very briefly, because there is another test function that appears quite naturally in this discussion, and the argument has been useful in other problems in geometric analysis. Okay, so essentially we're going to explore another key feature of two-dimensional surfaces with constant mean curvature, which are the holomorphic quadratic differential observed by Hoff in 56, right? And so essentially what you have here is that if you use complex coordinates on your surface, then this quadratic differential here is always holomorphic if your surface has constant mean curvature in a space form. So this comes from the Codazzi equations, right? And so that's a key property that you have for two-dimensional surface, and using that quadratic differential you can construct a flat metric on your surface by just taking the norm of this quadratic differential. So it's a metric that is flat, and flatness here just comes from the fact that the quadratic differential is holomorphic. Okay. On the other hand, if you look at this flat metric, you can notice that it can have singularities, right, which counts from the zeros of this quadratic differential form. In other words, umbilical points. So umbilical points are singularities for this flat metric. Okay. If you are, for example, dealing with a sphere, then in fact your sphere must be totally umbilical. So the case of spheres is well known, it's just the theorem of Hopf. Okay, and for other topological types of surfaces, then these singularities, these umbilical points, are always isolated, and in fact there are formulas that allows you to count the number of singularities in these surfaces. And it turns out that when your surface has genus 1, then there are no umbilical points. And so for tori surfaces, you have a very well-defined flat metric there that you can construct using the norm of the second fundamental form. And this has been useful in other problems in geometric analysis. Okay, so now that you know that this metric is smooth, this metric is also conformal to our original metric, right, by this conformal factor in terms of the function omega, right? So at this point I'm assuming that c plus h squared is always positive, but the cases where this is negative or 0, you can handle that in a very simple manner. Okay. So now you have these two conformal metric, and so one computation that you can do is to compute the Gauss curvature in terms of the function omega, and we have a formula for that. And if you look at this formula, you're gonna notice that the sign of the Gauss curvature is the same as the sign of this omega function, or in other words, in terms of the sign of the hyperbolic sine function of omega. And so if you want to study the flat tori, the one natural thing you can do is just to look at this hyperbolic sign of omega function, right? You try to study the sign, because if you prove a sign for that, then that will imply a sign for the Gauss curvature, and then by the Gauss-Bonnet theorem the surface will be flat. So essentially you want to prove a sign for omega, right? And the reason we can do that is because this function omega solves a very important differential equation, the sine-Gordon equation, which is given here, right? So essentially the description of genus 1 surface comes down to study the sign of this function of omega, right? And so if it does not have a sign, then you can do a variation of that surface and use that as your test function, the stability inequality, okay? And the reason you can get an information from the stability inequality is because it solves this very nice equation. So the key observation of Ritter and Ross is that hyperbolic sign of omega always decreases area up to second order when this function of omega changes sign. So if it does not change its sign, of course that implies the surface is flat, right? And so that is just a variation that you can do with this function just to make sure that it has average zero over the surface, but that won't break down this interpretation. And so that's how you prove the theorem we mentioned earlier. So we have the topological restriction in any spherical space form. We also have the geometric description that works in any space form, okay? And using that, Ritter and Ross gave a proof of the isoperimetric problem in RP3. So in that case, you have both geodesic spheres and tubes about geodesic as isoperimetric surface. So the tubes about geodesics are better competitors than geodesic spheres when the volume is, for example, half the volume of RP3, okay? And I would like to remark that this is the first example where the classification of stable CMC surface gave an application to the isoperimetric problem. Okay, so this is the result in RP3. As I mentioned earlier, we can extend the argument to other spherical space form, and that's exactly what we have here, right? So if you look at spherical space form whose fundamental group has order 3, which corresponds to those lens spaces, then you also have a characterization. The same description given by Ritter and Ross works in that case. And again, this is an application of the Willmore conjecture. And what happens to other spherical space form, right? If you look at lens 4, lens 5, the method breaks down in that case, and so the problem there is still open. So result that we were able to prove in this setting was concerning spherical space forms with large fundamental group. So in that case, we showed that geodesic spheres and tubes about geodesics are the only solutions for the problem. So essentially, in the proof of this result, we just need to rule out non-trivial topology because the description of genus 0 and 1 was already given by Ritter and Ross. Okay, so I'm not going to discuss the proof of this result, but I would like to state some key ingredients that is important in the proof. So the first ingredient is convergence for 3 manifolds. And notice that as the fundamental group increases, then the volume of your manifold goes to 0. So if you want to study the problem in these manifolds, you need to do some rescaling of your manifold. And once you do that rescaling, then using the Cheeger-Grom of convergence, we can make sure that we have a well-defined notion of convergence. And you can check actually that for the manifolds we are concerning here, the possibility for the limit can be either R3, a quotient of R3 by a cyclic group, or the rank 2 flat 3 manifolds, the product of a flat tori with R, right? So we don't have the flat 3 torus here because this convergence preserves topology when in the class of closed manifolds. Right, so of course one needs to be careful when doing this convergence, because if you use a very large scaling, then you're going to converge to R3, and then you might lose all topology and geometry at infinity. And so there are some care that you need to do in order to choose the scaling appropriately. Okay, and for that a key ingredient is the classification of spherical space form, which has been available for a long time, and using that classification we were able to understand what kind of scaling was appropriate when studying this problem. Okay, and finally let me mention that as soon as you take convergence for 3 manifolds, there is also convergence for the isoperimetric surfaces as well, right? And so this isoperimetric surface will converge to something in these limit manifolds. And remember that in the flat torus times R, cross R, there are examples of genus 2 CMC surfaces which are candidates for the isoperimetric problem in that setting. So you need to be careful analyzing the possibility for your limit. There is also the possibility that our limit is non-compact, right? So this is also something that you need to address. And for that we use a very famous result of Da Silveira, which gives you some kind of regularity for stable CMC surfaces. So essentially it shows that if you have something non-compact, then it must be totally geodesic. And this is indeed a key ingredient in our proof. Okay, so in the third video, I will address this problem of classifying volume preserving stable surface in the real projective space of any dimensions. See you in the next video. Thank you.